at least for us who come from Stony Brook. You can see in the back Jerry Quirk and Cassandra Heiselman. We're only missing Guan Chao Feng, but he's preparing for to attend another workshop that is coming up next week. So what I will be talking about is analysis of CTG signals by deep Gaussian processes, and I will keep my presentation on a fairly high level, and I hope that it will be informative for most, if not all of you. So let me start with first one definition of machine learning, which goes like this. So it's an area of data science, which is concerned about building algorithms that take as input informative data and produce as output predictions that are functions of the input data. So this term actually came about in 1959, machine learning, and it was not really used that much in the 60s and 70s. It was more popular term, pattern recognition. But then with the latest advances, especially in this century, it became extremely popular. So what we mean here by input data in our context here for this workshop, these are data that would be the FHR time series, the UA signals, the mother heart rate, any clinical data, anything that is informative about the fetus and the mother. And the outputs could be, or the prediction, obviously, is the well-being of the fetus, or anything that is of interest to the clinicians. So we here as people who work in the field of signal processing, machine learning, we just want to know what exactly is that clinicians would need so that we can actually provide the assistance that the computers can do with processing the data with the algorithms that we build. So what is inside the box, it depends. In previous years, before the deep learning era, we had these more classical approaches to machine learning. This reminds me on something that was happening in the 80s with artificial intelligence. Then the approaches were to simply mimic what people do. And this is what, still in many approaches that are used today, we still maybe want to mimic what clinicians do. And maybe that's not the right approach. So the opposite approach, or the alternative approach, is to let the machine decide in a different way what it should do in order to provide advice or assistance to clinicians. So there are two, in general, types of machine learning algorithms. Algorithms that can do classification. So, for instance, the simplest possible way it would be to classify, in our context again, fetuses that need immediate intervention, or one can wait for the delivery for the process to proceed. And the other one is to simply perform regression. Regression means that the output is a continuous variable, or a set of continuous variables. So classification, it simply means it's discrete. Regression, it simply means that it is continuous. So, as I said already, and this was mentioned in previous talks, we now live in the era of deep learning. And deep learning methods are machine learning methods based on artificial neural networks. And they're different from the neural networks from the 90s. I remember when I was assistant professor and attended a conference in San Diego, it was 1993, neural networks were still popular. And there was a panel with representatives from various funding agencies. And the first sentence that we heard was, please do not send any more proposals on neural networks. You haven't accomplished anything. You got all the money and no results were delivered, except for maybe one area, which was optical character recognition. Nothing else worked. And then again, fast forward to 2006, and then came the first encouraging results when people started to add more layers. So the networks that were not working the way everyone expected were too shallow. And then what the breakthrough was, by adding more layers, and what is more important, finding ways how to learn with so many more unknowns in the networks. That's what made the difference. So as you can see, in a deep neural network, you have many more layers. So the green nodes there represent nodes with inputs. The orange nodes are nodes with outputs. And everything inside are hidden nodes. And what neural networks do is, through training, they learn all these connections. They learn the weights. And there can be millions of weights. And what, as you very well know, in the past few years, there have been spectacular results where these kinds of networks can perform better than humans, sometimes in recognizing images. There are some spectacular results also in speech processing. Now, the bad side, there are two bad things. One is that these networks need many, many data for training. That's the first bad thing. The second one is they do not produce probabilistic results. You don't know how sure you are about what you're predicting or classifying. They just give you the result. Now, what I am actually interested in, and our work is pursuing, is not deep neural networks the way you saw on the previous slide, but to work on deep Gaussian processes. But first, let's take a look what Gaussian processes are. So it all started with Djuric from South Africa, who was a statistician and mining engineer, and he was interested in determining where in the area of interest he could find diamonds. Now you can afford to dig in so many different places to bore holes, and then based on the information you collect, you would like to decide where to go next and to dig. So this is what he started. He had a master's thesis, and his advisor was this Frenchman, who in fact put the theory in place. And but interestingly enough, this term, Causation, is only used in geostatistics. What it's the same thing. What is used today in statistics is Gaussian processes. So let us take a look what actually Gaussian processes do. Now, think that you have an input, again, x, that you observe, and then this x is transformed by some function f to an output y. So what is known here is only x and only y, but you don't know f. What the Gaussian processes will do for you is it will estimate that f. So rather than like what we know, what we do in classical estimation theory, we have one parameter, for example, to estimate, say, a mean value from data. Here, the goal is much more ambitious. We want to estimate functions. And the Gaussian processes do it in such a way that one has, for these functions, a prior, which is a Gaussian process, and then the data will change the prior to a posterior. And you'll see an example in a minute. So again, one has data as inputs x and outputs y, and one wants to estimate f. And for that, one has to have training data. And here's the beautiful part. Unlike deep neural networks, for Gaussian processes, you don't need many data. That's one advantage. The other advantage is everything goes through the calculus of probability, through Bayes theory. So all the results are probabilistic, as you will see now. So this is an example, a very simple example, where the function of interest is this sine x over x. So we don't know the function. So what we know is, we know these 6 or 7 pluses that you see, plus signs that you see. This is what is given to us. And now given this input and output data, so they're given these values of x and those values of y, we would like to estimate that function. Now what you see on the graph is the actual function, which is a dotted red line. And what you see in blue is the mean value of, because I said everything is probabilistic, is the mean of the estimate of the function. And you can see it coincides very well. What you also see is in this blue shaded region, this is the confidence you have about the function at these values. So here, you can see that at this value, you have a point, and here you have a point, and there are no points in between. And this is why you have lots of uncertainty there. Where you have the measurements, there's no uncertainty. Over there, there's no uncertainty. So, and everything is done in a principled way. There's no ad hocery. The only assumption is that the prior of the function is a Gaussian process. So I will now switch to results that we obtained using Gaussian processes. So in few of the talks, it was mentioned that in CTG data acquisition, we lose data, and what we do then is simply try to either interpolate, and I think I heard today linear interpolation. Well, one can interpolate, and this is what Gaussian processes do very well, is interpolation. After all, this is what Danny Craig was doing. He would dig holes in several places, and he would start interpolating and go to the next place where it was most likely to find gold or diamonds. So here you see two curves. At the bottom you have a description of how we are able to predict missing values when we only use the FHR signal with their uncertainties. So in this particular experiment, we had around 500 samples, and we removed 120 samples in different places. And then what, again, you see is the uncertainty. The uncertainty in this example also is a result of noise that we added on purpose to the measurements. What we also did now was we used the same data. So these are real data, not simulated data. The only thing that was added was just noise on purpose so that we could see the variances. Now, what we also did was we did the same estimation of the missing samples by exploiting the UA signal at the same time. And you can see now how actually we shrank the uncertainty about the missing FHR data when we use also the UA signal. So clearly, the UA signal is very helpful to tell us something about the FHR signal. So my recommendation for all of you who would like to, who need to interpolate, is use also the UA signal for that. So this is just more results on estimating missing data. So for instance, on the top you can see the mean square error. The red line is when one uses the GP-based method, and on the top is when one uses spline methods that are typically used for this purpose. So the Gaussian process outperforms the spline method. And similarly at the bottom. And more results on tables. You can see, for instance, the cubic spline has this error, 3.5, as opposed to a GP-based method that uses also UA, it's 0.3. So it's one order of magnitude better accuracy. So this is another interesting result that we were interested to learn more about it. One phenomenon that we wanted to learn more about, and that was to look at the cause and effect between the FHR signal and the UA signal. So, as you know, causality is quite tricky thing to discover, and here you have on the left side FHR signal, UA signal here, and what we have is we have been working on a method that allows us to find the direction of causation. For that purpose, what we do is first we find low-dimensional manifold of these signals, of the FHR signal and the US signal. It was mentioned several times throughout this workshop that the mother is like one system. And these signals, the US signal and the FHR signal, they are coupled. So the purpose of this work was to find how they are coupled. So here you can see that how the attractor manifold of the FHR, so for the three most important dimensions, and the same thing for the US signal. So now the belief was that, and there is a method how to find how they are, how they map to each other. And there's a method for that. And what I would like that you look at is only the right part. So here is actually the main reasoning about this method, how causation is determined. In the signal that is caused, there is signature about the causing signal, but not the other way around. So what you see here, if one of these curves converges to 1, that means that there is a causation. The red curve represents or shows that it is the UA signal that causes changes in the FHR signal. And the other one that does not converge is in the opposite direction. So in other words, there is no signature in the UA signal about the FHR signal. So since this is about deep GP, deep Gaussian processes, so deep Gaussian processes are constructed in the same way as deep neural networks. You keep adding Gaussian processes. So here is an input, Z, and then the output of the first Gaussian process becomes the input of the second Gaussian process, and so on. By the way, I didn't mention one thing. One Gaussian process is equivalent to one layer of a neural network, of those neural networks that you saw at the beginning, but it is infinitely wide, which is wonderful. So now you can think of this as deep neural networks with so many layers as you have notes here on this slide. So what we have done is we have used this deep Gaussian process to classify, and with 5 layers. What you see are the results after layer 1, layer 2, layer 3, layer 4, and layer 5. The shades of gray show how uncertain you are. The darker the screen is, the more uncertain you are. There are 2 classes of data here that correspond to, we used as labeling the pH value. So the blue circles and the red squares, and each axis represents 2 features from that space of the Gaussian process. So you can see now that in this last layer, the blue circles are clustered in one corner based on the features, and the red squares are on this side, which means that one can easily classify them if one uses, for this particular case, 5 layers. So the system was not able to do it after few layers, but after 5 layers, it was much easier. So the reason for this capability by adding more layers is that the machine learning method becomes much more, increases its capacity to learn and to classify or to predict. We have also done comparison between the SVM and the deep Gaussian process. We used a check database for this, and you can see the results where we use the geometric mean when of the specificity and sensitivity, and we can see that in comparison to the SVM method, the deep GP worked better. Now, I have to say that for this particular work, we used the features that were mentioned in the previous lectures, like time domain features, frequency domain features, nonlinear features. We have not explored yet approaches just based directly on raw data. As I said, we would like to go away from, we will not ignore that. All the knowledge that has been acquired so far about classification of data, but we would like to provide the opportunity of the machine to learn on itself and decide how to classify or how to predict without imposing the features that have been used so far in practice. So I would like to conclude with these thoughts. So first, I believe that the deep Gaussian processes offer a very intriguing alternative to deep neural networks as a platform for predictive analytics. They're not data hungry, as I mentioned. Their results are interpretable. They're also in the form of probability distribution. That is also very important. They work within the Bayesian framework. And finally, the US signals are very informative for classification and prediction. And thank you for, obrigado, for your. This is Cassandra in action.
Oh, yes. Oh, first I was looking at the pregnant one. Yes, thank you very much. This is very educational. And thank you very much for sticking to time. That was great. Keep questions coming. Well, you're coming down anyways. You're next. So make
Okay, Gaussian process is a stochastic process. Stochastic process is a family of random variables of infinite number of random variables. A random vector is a vector with finite number of random variables. Stochastic process has infinite number of random variables. So then, whichever variables you pick, they have Gaussian distribution. That's what a Gaussian process is. I was told not to go too technical, so.
Peter, thank you again so much. That was really clear and short. Both of those things are unusual. Could you tell us a little bit more? Because I don't know if you did it there, but I'm assuming there was a test case and a validation that also went on in this process to help you get to those levels of sensitivity and specificity. I don't know if that was true, but if it was, how do we? One of the issues I'm trying to deal with is how I then put all of these same findings in different contexts. So, for example, my data from South Africa they're in a little bit of a different context. The biology and physiology ought to be about the same, but there are other factors that are going to change these input-output relationships. So going from, for example, the UK data we have to the States data to South Africa presents another layer of difficulty. Wondering how you're thinking about dealing with that.
So the first, the answer to the first question is that we use as a ground truth the pH value. So it is really a very sticky point in our, at least, work, what a ground truth is. What exactly are we trying to, and how we evaluate the accuracy of what we do. All these machine learning methods are methods based on training. So you have two types of training. They can be supervised or unsupervised. Supervised means you have the input, you have the output, and unsupervised means you don't have the input, but you have the output. So, but what is the output? That is something that we need help for. We, the group who is in charge of signal processing.
Thank you.
As for the second question, these methods are capable to adapt to. So if the data are of somewhat different type, then one has to rerun the training process, and they'll get a different function with different parameters. And
but one of the good things is you don't necessarily start from scratch with these neural methods. You know, you use what we call transfer learning. Am I right? That applies to Gaussian processes as well. So you've learned on this data, and then you improve it with your additional ones.
Yes, these VGPs are hierarchical. Yes.
So you could partition your North American and European data, for example, because they might have different characteristics.
It could be that they have different characteristics.
So, thank you very much.
can take. Jerry, put this in your bucket. Oh, sorry. Sorry.
So last but not least, I've orchestrated Jerry to
Oh, okay.
fly from US and give us his hopefully
As much-
personal reflection.
As Monty Python would say, and now for something completely different. I was asked to just communicate what my feeling and sense about CTG, fetal monitoring, and where we've been, where we are, where we're going. And I must say that over 40 years,